All right, so welcome to Thursday, July the 2nd. For the Canadians out there, happy Canada Day yesterday. And even though it was a quieter than normal celebration, no parades, no fireworks for the most part. And for our American friends coming up, welcome to, looking forward to July 4th this weekend. So welcome to our 12th session of the virtual environmental ergonomics series, and I want to welcome you again on behalf of our co-organizers, Chris Tyler, Tadej Debovich, and myself, Stephen Chung. As I said, today is going to be on metabolism and hypoxia, and we're looking forward to this. This will be, of our series so far, our fourth one actually dealing with different aspects of hypoxia or altitude. We started off in the very first session with Mike Timko talking about the challenges and logistics of high altitude expeditions. And we also touched on altitude training in a world-class athlete, talking about both altitude and heat adaptations for Evan Dunphy leading up to his World Championship race walk performance in Qatar last summer or last fall. And then we also had a specific one looking at hypoxia and its effect on muscle mass regulation in June, along with looking at the role of nitric oxide in altitude adaptations. And then that finished off with last week. We had a great session on cross adaptation, looking at adaptation between especially heat adaptation transferring over to hypoxia and altitude adaptation with Ollie Gibson, Becky Rendo, and Alex Zoteridis. So just to let you all know, all of our past talks are available at ICEE.com, or sorry, ICEE2021.com under the past talks link. So you'll see, for example, this screen, and that'll take you to the talk on the, if you click under the pictures, and then also the underlined, the hyperlink there will take you to a student guide that has been prepared that you are more than welcome to use as if you use this for instructional purposes. Coming up, we obviously have today on hypoxia and metabolism. Just to let you know, we're going to take a break next week because there is the Futures Physiology Conference organized by the Physiological Society, and much of it deals with environmental stressors on physiology. So we figured that would be of high relevance and interest to many of our audience. And then we're going to finish off this series for the spring and summer with looking at Tokyo 2020 and the effects of adverse weather and the planning for it. So we will be starting up again in the fall. We would really appreciate if you would go to ICE2021.com and fill out a feedback survey telling us what you like about this, what we can do to improve as we plan to return in the fall. So that's the intro, and I'm going to stop sharing my screen and introduce our speakers. The first one is Dr. Claire Berryman from Florida State University. And stop share. All right. The other thing, as Claire is setting up, the main way to interact with us is using the Q&A tool that you'll find down at the bottom right of the menu bar. So with that, Claire, the floor is yours.
Okay, great. Thank you. And I'd like to thank the organizers for the invitation to present some research. And today I'll be talking about dietary carbohydrate recommendations at high altitude. My background is a picture taken in Colorado Springs of Pikes Peak at 4,300 meters, where a lot of the early high altitude studies were conducted in the US. So, like I said, I'll be talking about dietary carbohydrate recommendations. And I just wanted to list a few here taken from review articles, book chapters, and technical bulletins. None of the recommendations are specific to carbohydrate consumption during exercise versus rest. They're more general recommendations. The first one is from an article in ACSM's Health and Fitness Journal. And it reads that it's recommended that complex carbohydrates make up greater than 60% of total caloric intake at altitude. A quote taken from a book chapter by George Brooks in Human Adaptation to Hypoxia states that the previous recommendation of increasing daily energy intake above appetite by emphasizing carbohydrate-rich foods remains the recommendation. And finally, a recent article in Annual Review of Nutrition states that carbohydrate intakes greater than or equal to 55% of total energy are needed to fuel energy metabolism at high altitude. And so we also have more formal recommendations for carbohydrate intake at high altitude. This table shows recommendations for nutrient composition of combat rations for the NATO response force. And you can see the various columns are organized by civilian norms, normal operations, combat operations, and then extreme environments. So obviously for this talk, we're focusing on recommendations for our nutrient composition recommendations for high altitude. And you can see in this column that the recommendation is to consume, or it's recommended that the composition of the combat rations contain 4,700 calories, which is about 1,100 more calories than what we see in combat rations for normal operations. And the majority of those calories are, it's recommended that they come from carbohydrates. So the recommendation is to include greater than 700 grams of carbohydrate in these rations. And then finally, the US Army has developed a supplemental combat ration that's to be used in conjunction with the normal combat rations. So here in the picture is the US military's MRE package, so combat ration, and the components are also shown here. The supplement ration is called the Modular Operational Ration Enhancement, abbreviated MORE, and this ration supplement is specified for high altitude and cold weather. And so it contains, the purpose is to increase the amount of energy provided to the soldier, but you can see based on the items here, so these are the 3 different packs that are available for the MORE ration. And you can see the items in these packs are items that are high in carbohydrates, including caffeinated pudding, energy gels, and carbohydrate enhanced beverages. And finally, this quote taken from the Department of the Army Technical Bulletin states that the preferential use of carbohydrates in a hypoxic environment is supported by the fact that carbohydrates provide the most energy ATP per molecule of oxygen transported through the electron transport chain. Thus, in a low oxygen environment, carbohydrates are the best fuel source. And so, what's the scientific basis for these recommendations? Most of the recommendations, or people talking about increased carbohydrate needs at high altitude, will cite this paper that was published by Brooks and colleagues. And for this study, they took 7 healthy males and used both stable isotope tracers and AV balance techniques to evaluate glucose kinetics during rest and exercise at sea level, acute high altitude, and chronic high altitude. And in the panel on the left, panel A, we have rate of appearance of glucose in the blood, and in panel B, rate of disappearance of glucose from the blood. And you can see I've labeled the glucose kinetics at sea level, acute altitude, and chronic altitude. And of greatest interest is this chronic high altitude, where the rate of appearance of glucose in the blood is almost double that at sea level, and that increases during exercise and is significantly higher during chronic high altitude. The rate of appearance of glucose in the blood is significantly higher at chronic high altitude compared to both acute altitude and sea level. And when we look at panel B, the rate of disappearance of glucose from the blood, these findings mirror those of the rate of appearance. And so we can look at the graph on the right and see this is showing the metabolic clearance rate of glucose. A greater clearance rate is indicative of glucose removal and use by the body. We can see that during chronic exposure, this is greater during rest compared to both acute and sea level conditions. And then during exercise, we see this dose response stair-step effect where the metabolic clearance rate is higher at acute high altitude and even higher at chronic high altitude compared to sea level and acute high altitude. And so overall, this data suggests greater dependence on the use of blood glucose during rest and exercise at high altitude. So if we put these findings into practice, have we been able to show a performance benefit of consuming carbohydrates during exercise at high altitude? And this study by Fulco and colleagues was a time trial done at sea level and high altitude. They provided, they had individuals during the time trial. They did, before the time trial, they did 40 minutes of fasting steady state exercise on a cycle ergometer and then a self-paced maximal effort time trial. And the max effort continued until participants completed 720 kilojoules of work. And they completed the sea level test twice, and then also on day 3 and day 10 at high altitude. And so one group was randomized to consume 10% carbohydrate solution and the other a non-calorie placebo supplement at the start of the time trial. And then they consumed that every 15 minutes throughout the time trial. And so on the left panel, we see time to complete the time trial and then the different conditions along the x-axis. And during the sea level condition, consuming carbohydrate did not improve performance, but at day 3 and day 10 at high altitude, the carbohydrate group completed the time trial faster than those in the placebo group. So this would suggest a performance benefit of consuming carbohydrate at high altitude. Unfortunately, when they tried to replicate these results in a group of moderate altitude residents, taking those individuals up to high altitude and doing a similar time trial, half the group supplemented with carbohydrate, half with placebo, they were not able to replicate the results and did not see a performance benefit of consuming carbohydrate in that group. Similarly, in a study that our group conducted, we looked at the performance benefits of consuming a carbohydrate supplement, 145 grams of carbohydrate during an 80-minute steady state exercise bout prior to a treadmill time trial, a 2-mile time trial. And in that study, as opposed to the Fulco study, where they consumed the carbohydrate beverage throughout, in our study, we had them consume the carbohydrate beverage before they completed the time trial. And this graph is showing on the y-axis time to completion, and then our different conditions. And we saw a decrease in performance at acute high altitude and a slight improvement at chronic high altitude, but those times never reached the level of performance at sea level. But in all of those conditions, we did not see a difference in the supplement group. So there was no benefit of consuming the carbohydrate beverage in any of those conditions. And so whether that's due to the intensity of the workload or the ability to utilize exogenous carbohydrates, we don't know, but a little window into what we did see when we took glycogen, measures of muscle glycogen, we saw a decrease in muscle glycogen from pre to post in each condition, but did not see any differences in the carbohydrate versus the placebo supplemented group. So again, just supporting these findings that there was no glycogen sparing effect of the carbohydrate. And again, I mentioned the exogenous carbohydrate because Lee will be talking more about our ability to use exogenous carbohydrates at high altitude in his talk. And so the differences between this study and the full coast study could be due to the mode of exercise, the duration of the time trial, whether the carbohydrate was consumed before or during the exercise bout. So there's a lot of differences between the two studies, and that's kind of the theme of altitude research. There's a lot of differences in study design and application, and kind of hard sometimes to compare studies side by side, but basically the inconsistencies of these studies on performance means that we have more work to be done and just need some more research in this area. And so the next thing I want to talk about is just some considerations for interpreting studies conducted at high altitude. So we've already somewhat covered the acute versus chronic effects of high altitude with the Brooks study showing greater glucose utilization by the muscles at chronic high altitude compared to acute high altitude. With the performance measures, we also showed a difference between acute and chronic exposures where there is definitely a performance decrement upon acute exposure, and then that performance decrement is somewhat attenuated with chronic exposure. But just an important consideration is thinking about the length of exposure to altitude when interpreting these studies. Another consideration is altitude is absolute versus relative intensity of exercise. So I won't spend a lot of time on this point because this will be a focus of John's talk, but I do think it's important to think about carbohydrate or think about this point when interpreting studies on fuel utilization at high altitude. And so this figure is showing the crossover concept where as exercise intensity increases, the proportion of energy coming from carbohydrate also increases with a concomitant decrease in fat utilization. So if we use the Brooks study as an example, the participants exercised at 100 watts, which was about 50% of sea level VO2 max. And this means based on this figure, they would use about 40% fat and 60% carbohydrate to fuel their exercise. But we know at high altitude, VO2 max is about 25 to 30% lower than at sea level. So although Brooks matched absolute intensity at 100 watts, the intensity is greater, the relative intensity is greater because of the lower VO2 max at high altitude. So in that paper, they report that participants were working at 65% of high altitude VO2 max. And In this case, and based on the figure, they would use about 30% fat and 70% carbohydrate to fuel their exercise. And so given this concept, it's not entirely surprising that more carbohydrate was used at high altitude. But I should say, whereas the Brooks used absolute intensity, and many of the studies I'm talking about used absolute intensity, there's just as many studies using relative intensity of exercise. And whether absolute or relative intensity exercise are compared, it really depends on the research question, whether you use absolute or relative intensity in the study. Another consideration is energy balance versus energy deficit. So in the Brooks study, the volunteers were in energy balance, but that's a rarity. When individuals go to high altitude, they're often in energy deficit. This was a study that we conducted recently in which we placed individuals in an energy deficit through caloric restriction and increased exercise. We put them in a 40% energy deficit, but because of increases in basal metabolic rate that occur at high altitude, we saw that they were in a much greater energy deficit. And you can see in the picture, the graph on the right here, that over 21 days, over their time at high altitude, which was 21 days, there was a decrease on average of about 8 kilograms of body weight. So these individuals were in severe negative energy balance. And so that has to be taken into consideration when we look at results in fuel utilization in these individuals. So for example, when we ran steady state exercise tests at sea level and high altitude, in our individuals, we saw, this is the carbohydrate, the gram amount of carbohydrate oxidized during exercise in the various conditions, and then whether they were in the carbohydrate or placebo supplemented groups. And so in our study, we saw that carbohydrate oxidation decreased at acute high altitude and then decreased even further at chronic high altitude. And then we saw the opposite effect on fat oxidation, with increased fat oxidation at acute high altitude and in even greater increases in fat oxidation at chronic high altitude. And that could be that our subjects were in such an energy deficit that they became fat adapted. So just another important consideration. It's important to think about the differences between men and women. Most of the studies conducted at high altitude have been conducted in men. This study, I don't know of any studies comparing men, the effects of carbohydrate intake or fuel utilization, comparing those effects in men and women directly. This study was conducted in women only and shows the opposite effect of what we saw in men in the Brooks study. So the left panel is showing rate of appearance and rate of disappearance. And at rest, we'll just look at the black bar, which represents sea level, rate of appearance of glucose, and the white bar, which represents day 10 at high altitude. And we see that rate of appearance of glucose in the blood was decreased in these women when they went to high altitude. And the same occurred for the rate of disappearance. And you'll remember in the Brooks study, we saw an increase in glucose rate of appearance. And then again, different than what we saw in the Brooks study, these women had no difference from sea level to high altitude in the rate of appearance of glucose, where Brooks saw that dramatic increase in rate of appearance of glucose. And this is The same point is illustrated here with the respiratory exchange ratio. And again, differences were seen at rest. A lower respiratory exchange ratio would suggest more fat oxidation, a higher number, more indicative of carbohydrate oxidation. And so we see at high altitude, the open circles, a lower respiratory exchange ratio compared to at sea level. And again, those findings are contrary to what Brooks found in men. Okay, and the final consideration is just the magnitude of elevation. And this is pointed out really nicely in a review by Trent Stellingworth, where they point out that we have pretty substantial evidence to suggest increased glycogen use and carbohydrate needs at extreme and high altitudes, but the research is lacking at more moderate and low altitudes. And importantly, athletes going to training camps or military personnel training at military bases or during operations maybe or are going to lower elevation, so low altitude or moderate altitude, as opposed to these really high or extreme altitudes. So it's important that we do research at low and moderate altitudes to better understand if there are increased carbohydrate needs at these lower altitudes. And with that, I'll just leave you all with a few concluding remarks. At high altitude, it's important to increase energy intake to meet increased energy demands. Appetite may not always accurately, or usually will not accurately reflect true nutritional needs. And I would say it's important to prioritize carbohydrates, but also important to not neglect protein and fat. And with that, I'd be happy to take any questions, and my email address is listed there. And I'd be happy to take questions there as well.
All right, thank you very much, Claire, for a great intro talk, talking about, again, the effects of carbohydrates, both the need and the and kind of the actual use of it. One quick question just to start off is, in those studies where there's been supplementation, has there been, is it calorie matched, or is it just the fact, or could those responses be simply due to just more fuel being available, period?
Yeah, that's a good point. Those studies were not calorie matched.
Okay, and I guess what would you think the implication would be if it was, whether it's with, obviously it would be matched with either like a fat or protein mix, or like, would you have any, what would be your ideas how those things might respond if they were matched?
Right, so I guess it would depend if the individuals were fat adapted. In that case, maybe providing some fat would be usable, but we know from other studies at sea level that fat during exercise is going to slow gastric emptying, and some of that fuel may not get to the cells. And so it's hard in nutritional studies to think about when you decrease one macronutrient, if you want to match for calories, what macronutrient do you increase in its place? I think that, yeah, that's a hard question. I'm trying to think, maybe, well, you could look at different mixtures of carbohydrates. So you could do fructose glucose mixture versus maltodextrin, something like that. But yeah, it gets really tricky when trying to match for calories.
Certainly. I guess, well, there's a couple of questions that are along the same lines of talking about kind of semi kind of what we would think of as chronic, of people adapting to altitude versus kind of lifetime residents. Maybe we can touch on that kind of in the group panel. I'm sure there'd be good responses and feedback or a discussion there. I have another question we'll finish off with from Phil Ainsley. And one of things he talks about is with acute exposure to hypoxia, there's often hyperventilatory responses, which can affect the RER values and also the partial pressure of oxygen and alveolar PO2. How might that kind of affect some of the results, especially if some of the work may be predominantly using metabolic kind of measures rather than kind of actual direct muscle measures or kind of direct fuel use, for example?
Yeah, and that's going to be more of an issue at acute high altitude. But yeah, the hyperventilatory effect is definitely not going to be accounted for in those acute measures. So that's a really good point. And I think that's why the Brooks paper has also stood the test of time using those stable isotope and AV methods, because it's not dependent on, respiratory exchange ratio or other indirect calorimetry measures. So that's, a really good point that has to be taken into consideration, particularly for those acute measures.
All right, super. And obviously your point about different potential difference between males and females is super interesting. And there was a couple of questions on that. And I'm sure maybe that would be a good kind of overall discussion we can have at the end too. So I will save those questions. And again, in the interest of time, I'll move on to our next speaker. Thank you so much for that, Claire. Our next speaker is Dr. John O'Hara from Leeds Beckett University in the UK. And I'll pass the stage on to him.
Yeah, just get this slide sorted. There we go. Internet crashes just as we want it to work in a second. But just whilst that's trying to sort itself out. So whilst that's trying to sort itself out, so I'm John O'Hara, a professor at the Leeds Beckett University within the Carnegie School of Sport. I'm director for the Centre for Human Performance there at the moment. And my talk today is going to be based on exogenous and endogenous fuel use in men and women at high altitude compared with sea level during exercise at the same relative exercise intensity. So hopefully we'll pick up on maybe a couple of the issues around men versus women as we go through this talk. Thank you, Claire, for your presentation. I think that's laid the groundwork really nicely for what myself and I think Lee will talk about in our presentations. Obviously, with high altitude exposure, we get a decrease in the amount of oxygen we're able to carry in our blood, known as hypoxia, and this is likely to affect fuel selection. And as Claire's outlined, it's probably really important for us to understand how altitude affects fuel selection, because that may have an impact in terms of what nutritional recommendations we make to either athletes, mountaineers, or military personnel. And I suppose the literature has very much assumed that at altitude carbohydrate oxidation would be increased due to fat oxidation requiring more oxygen per molecule of energy synthesized than the complete oxidation of carbohydrate. Now, that premise fits in certain circumstances, but I'm going to present some data within the presentation which challenges that assumption and trying to unravel why we found what we found with some of our studies. And really what I'm going to do now is provide an overview of our research in this area. And what I'm going to start off with is I've made that sort of bold statement about assuming that altitude increases carbohydrate oxidation, and said that we'll present some data that doesn't fit with that assumption. But it's worth saying that that assumption is essentially correct when we're talking about the same absolute exercise intensity, when we're matching that at altitude and sea level. So if individuals are cycling at 200 watts at sea level and 200 watts at altitude, then yes, carbohydrate oxidation has been shown to be significantly higher. And this slide demonstrates that really nicely. And this is data from Alex Griffiths, one of my colleagues and previous PhD students, that published a nice sort of meta-analysis looking at some of these components. And we can see respiratory exchange ratio on the plot on the left, and carbohydrate oxidation as a relative contribution to the total energy yield on the right. And they both clearly show that carbohydrate oxidation is higher when we match the absolute exercise intensity between altitude and sea level conditions. And generally, we found within the meta-analysis that this isn't moderated by things like sex, carbohydrate ingestion during exercise, the actual altitude you're at, or feeding status. And this is likely to be due, we feel, to the dominant exercise effect with an increase in exercise stimulus when you're exercising at the same absolute intensity at altitude. And I suppose we can depict this, and Claire's already alluded to this, that we have this absolute and relative exercise intensity conundrum in terms of which one is the best one in terms of trying to establish what's happening with fuel use at altitude, and which one to use most effectively to provide the most, the best guidance in terms of nutritional advice. And from our perspective, we're very much of the premise that the relative exercise intensity is the best format in which to design the research to provide the right answers in terms of nutritional advice for athletes or military personnel or mountaineers. And this is very much based on the premise that as we go to altitude, our maximum oxygen uptake is reduced. Therefore, we would struggle to maintain the same absolute exercise intensity. And therefore, we naturally adjust our exercise intensity to be at the same relative exercise intensity. So the example here on the graph, we can see if we were cycling at 200 watts at sea level, that would be around 50% VO2 max. If we were to do that at altitude with the reduction in maximum oxygen uptake, then that would likely to be around 75% of VO2 max. So straight away, we know that if the relative exercise intensity increases, carbohydrate oxidation will go up. In sea level conditions, therefore, we would assume the same at altitude, and that has a really strong influence. Now, our premise is that we could work at 200 watts at altitude, but actually we'd probably moderate that and adjust that because we couldn't continue that for a prolonged period of time. So we naturally match the relative exercise intensities, which is why our work has gone down that line. And what's clear is when we look at matching relative exercise intensity, but the literature isn't clear. There is some literature that will say that carbohydrate ingestion goes up, some that says it doesn't, some which I'll present will suggest actually carbohydrate oxidation goes down. But what we're really interested in is consuming carbohydrate at altitude. We know from the sea level data that we can try and carbohydrate ingestion, we can try and protect our infinite stores of muscle and liver glycogen, and therefore try and enhance performance. And so this is a key bit of interest that our research group and Lee Margolis and Claire's and Andrew Young's research group are interested in at the moment. And there's real limitation in terms of research in this area. I think there's only 5 papers that have looked directly at carbohydrate metabolism during exercise when a carbohydrate beverage is actually consumed, using a mixture of techniques to look at fuel selection. The original work was by Berryman in 2006. So before I move on to our work, it's always worth, I think, looking at the starting point as such. And if we look at Berryman's work, he ran a protocol where people exercised at around 75% VO2 max for a prolonged period of time, and using 13 carbon tracing techniques, he looked at quantifying total and exogenous and endogenous carbohydrate oxidation. And what we can clearly see from his data is that when we match the relative exercise intensity between normoxia and hypoxia, carbohydrate oxidation goes up in terms of whole body carbohydrate oxidation. There's no effect on exogenous glucose oxidation. Endogenous carbohydrate oxidation goes up as well. So the increase in whole body carbohydrate oxidation is due to an increase in endogenous carbohydrate oxidation. Now, this is a bit intriguing in the fact that, well, if endogenous carbohydrate oxidation goes up, does that leave us short of glycogen and muscle in the muscle and the liver for prolonged exercise? That's probably not a good thing. But this started our intrigue off in terms of how can we sort of move this literature forward and to look at alternative carbohydrates. So Perrine used glucose. The sea level literature clearly shows that glucose and fructose that uses separate intestinal transporter systems means that we can get more carbohydrate into the system, and therefore has been shown to be more optimal in terms of fuel selection and performance at sea level. So we looked at designing a study where we could specifically look at glucose and fructose ingestion during exercise at terrestrial altitude. And what we did is we moved essentially our research lab from Leeds up to the Torino hut for a few days, and we exercised people for 2 hours. We had 7 men and five women, and we kept them separate within our analysis and used indirect calorimetry combined with 13 carbon tracing techniques to look at exogenous and endogenous contribution of carbohydrate oxidation. And we really wanted to look at the liver and muscle contributions, which is something that Perrine's study hadn't done. It just gave us an overarching suggestion that endogenous carbohydrate oxidation would increase. But actually we were keen to understand, well, is that the liver contributing to that change or the muscle, or would something different happen? And the exercise protocol we used is outlined here. People cycled for 2 hours. We did a gradual warm up, then they did 55% maximum oxygen uptake for 105 minutes. We collected blood samples every 15 minutes, expired air samples. We gave them a carbohydrate beverage equivalent to 1.8 grams per minute with glucose fructose in a 2:1 ratio, which we enriched with stable mass isotopes. And stable mass isotopes are a fantastic way of us actually tracing how much of the carbohydrate we've actually consumed during the exercise and establishing how much of that has been used as an exogenous source of fuel, which then allows us to do calculations for endogenous carbohydrate oxidation. And we did that at an altitude of 3,375 meters at the Torino hut in the Alps versus our lab back in Leeds. And this table of data here sort of identifies some of our findings. So total carbohydrate and fat oxidation is presented here for the full 2 hours of exercise in the men. And what we can see, which is really intriguing, is that at altitude, our carbohydrate oxidation massively decreased, and our fat oxidation in this group actually increased. So we got a greater reliance on fat when we have carbohydrate at altitude, which goes very much against what Perrine found. Now, some may argue that that's due to the absolute exercise intensity being lower at altitude, and therefore the total energy expenditure being lower. Yes, total energy expenditure was lower, but that doesn't account for the magnitude of change that we've seen here. So this data was really intriguing for us. And here's some of the other data. So this is 4 panel plots. In the top left corner, we can see exogenous glucose oxidation. And then we've got plasma glucose oxidation, liver glucose, and muscle glycogen use. Plasma glucose oxidation is a summation of exogenous and liver glucose oxidation. And we can see for exogenous oxidation that generally at altitude, that it was lower compared to sea level conditions. The rates are only significantly different at a couple of time points. But that's something around why that might be happening is something that Lee Margolis will pick up in his presentation after mine. Nothing really happening in terms of differences in plasma glucose or liver. It's quite large differences with a trend for muscle glycogen to be lower at altitude in terms of rate data. Highly variable data set. Effect sizes were very large, but statistically the rates weren't significant. But when we then look to normalize the data set in terms of the total energy expenditure and look at the relative contributions to total energy yield, we actually again support the fact that these data support the fact that fat oxidation was essentially twofold compared to sea level conditions, and muscle glycogen was significantly different on this occasion. So we got a significant reduction in muscle glycogen at altitude compared to sea level, with no differences in glucose release from the liver and exogenous carbohydrate oxidation. So our conclusion from this study was that when matching the relative exercise intensity during exercise, hypoxic exposure, during hypoxic exposure, fat oxidation is increased compared to sea level, with a concomitant reduction in the use of pre-existing muscle glycogen in men. Now, is there a possible explanation? When we were looking at that at this point, and looking at this in terms when we were writing this publication, we very much sort of leaned on some of the mechanistic approaches to this, and these need to be researched to establish whether or not they are actually what is producing some of the data that we're seeing. But obviously we know that with hypoxia, HIF1 alpha is increased, which will control PPAR alpha, which is a fatty acid activation transcription factor, which has an effect upon the upregulation of PDK, which impairs pyruvate dehydrogenase, and therefore essentially facilitates greater fat oxidation. And because we conducted our study in the fasted state, then that HIF1 alpha response might be slightly heightened in the fasted state as well, which may explain the difference between our study and Perronet's, and the fact that Perronet's study was a fed state, whereas ours fasted. And that may be a moderator in terms of us seeing differences in fuel selection at altitude, which is something I'll come back to in a little while. We separated the women within our study based very much on the fact that we know at sea level that fuel uses kinetics are different, in the fact that women generally burn more fat than men due to higher body fat percentage, greater lipid content in muscle fibers, better mobilization of free fatty acids from subcutaneous adipose tissue, and linked to obviously to seeing cyclic changes in estrogen and progesterone. And also Claire's presented some data from Braun's group as well that suggests that at altitude women burn more fat than men. So therefore we did our analysis with this group slightly separately. They went for exactly the same exercise protocol, and what we found is that total carbohydrate actually decreased, but on this occasion it wasn't sufficient to be significant, and there was no change in fat oxidation over the 2 hours of exercise in these women either. So very different to the men, but not this high, massive change in fat oxidation that we saw in Braun's paper. And if we look at our panel plot, looking at the rates of exogenous and endogenous oxidation, what's interesting is when we look at exogenous oxidation, on this occasion, each time point, glucose oxidation from the exogenous source of glucose and fructose was lower, and significantly lower. There was no real difference in plasma glucose or liver glucose output, nor was a difference in the use of muscle glycogen in these women, again contrasting to our males paper. When we normalize the data, we can see that actually there are no significant differences in the different relative contributions of fats and exogenous and endogenous carbohydrate sources to altitude compared with sea level. And we wondered whether or not, and the lack of change in fat oxidation in the females here was very much due to the fact they already had a 50% contribution of fat at sea level, and really we're seeing this sort of baseline effect where they've got nowhere else to go. And so our conclusion from that study was that exogenous carbohydrate oxidation was reduced in acute hypoxia, leading to lower absolute whole body carbohydrate oxidation. It's slightly wrong, isn't it, that conclusion? apologies, my conclusion is slightly wrong, but we saw a lower exogenous oxidation, but this the acute hypoxia, but that didn't really lead to a lower whole body carbohydrate oxidation at high altitude in these women. But what was really interesting is that Claire identified that there hasn't been a paper that's done a direct comparison between men and women, and that's not something we've written up as a direct comparison, but we're able to make a direct comparison because we've got the same participants under the same control conditions, doing the same protocols. And what we actually found is comparing their fuel use responses at altitude, their responses are identical. So the men shifted massively in terms of increased fat oxidation, and the women didn't, but their fuel kinetic responses are the same at altitude when they can, on acute exposure, when they consume glucose and fructose, which we found really interesting. Now, after this point, we recruited Alex Griffiths to do a PhD with us, and we felt that there was a lot of mileage in undertaking a good systematic review and meta-analysis in this area to establish whether there were any moderators in terms of what happens to fuel during exposure to high altitude. And so I've presented the absolute data, but in terms of the relative data, he's presented that nicely here. And again, on the panel on the left-hand side is to do with respiratory exchange ratio. The panel on the right-hand side is depicting decreased relative carbohydrate oxidation. And what's clear is that there is a mismatch in terms of studies. Some show a decrease in carbohydrate oxidation, including our studies. Some show an increase, some show no difference whatsoever. So when we're matching relative exercise intensity, the picture is not as clear as it is when we're matching absolute exercise intensity. Now, his analysis then went on, as it would do for a meta-analysis, to look at moderating factors. And he looked at feeding status before exercise, fed or fasted, looked at sex as a moderator, looked at the consumption of a carbohydrate beverage or not during exercise, looked at different elevations of altitude, looked at the type of altitude, whether it's terrestrial or whether it's simulated, and also looked at exercise intensity. And what he found was that the potential moderators through the meta-analysis were to do with feeding status, which I've already alluded to as a potential explanation to the differences between our work and Perronet's work, and exercise intensity. And so the next step after that was for us to design a study which would then start to have a look at these moderators. And so we designed a study which was performed at sea level and at 4,300 meters of simulated altitude. And we looked at giving individuals breakfast under each environmental condition and breakfast omission under each environmental condition, and looking at whole body carbohydrate and fat oxidation during prolonged exercise with increasing relative exercise intensity from 40 to 50 to 60%. And what we found was, also we can see is on the left hand side, we've got our relative contributions of carbohydrate and fat oxidation with 40% at the top, 50% in the middle and 60% at the bottom. And we can see here where we've got hypoxia with breakfast, normoxia with breakfast, hypoxia fasted and normoxia fasted. And what we found is the relative contribution of carbohydrate was reduced in hypoxia compared with normoxia after breakfast omission. So we had this reduction in carbohydrate oxidation when we didn't have breakfast, but there were no differences when we actually consumed breakfast, which suggests that actually breakfast consumption or feeding status is quite a key moderator in terms of what happens to fuel selection and whether that changes during prolonged exercise at high altitude. In terms of exercise intensity, the response wasn't consistent. So there was so at the moment, we're suggesting that actually the exercise intensity is probably not a key moderator when we're looking at exercise intensities between 40 and 60% of VO2 max. And so our conclusion from that study was that feeding status is a moderator of substrate oxidation at high altitude, but exercise intensity is not. But we're also interested in carbohydrate ingestion. So do we get the same effect when we control or manipulate feeding status and consume carbohydrate? And so what I'm going to do is very quickly share some data which we've not published as yet, but we've presented in some abstracts and conferences so far, but I'm not going to go into full detail as it's not fully published as yet. But we designed a study where we looked at carbohydrate supplementation based on feeding status. And so we had 4 conditions. All 4 conditions are altitude. 2 conditions were carbohydrate orientated, 1 with breakfast, 1 without, 2 were placebo, 1 with breakfast, 1 without, which are depicted here on the chart. What was unique about this study is actually we enriched the placebo with a 13 carbon tracer, so we were able to establish liver and muscle contributions to carbohydrate oxidation during exercise from the placebo conditions, and to see whether they would be different between the fasted and the fed state, and whether they would be different compared to the carbohydrate consumption during exercise conditions as well. And these data suggest that carbohydrate supplementation may only be effective at altering substrate oxidation while participants are fasted. Again, coming back to this idea that feeding status is a really strong moderator in terms of how our body reacts to consuming carbohydrates or not at altitude. We also found that carbohydrate supplementation when fasted actually matched the carbohydrate oxidation after breakfast consumption and placebo. So essentially it gave us, if we hadn't had it made no difference to whether we consumed breakfast or not. But what's also interesting is we observed a liver glycogen sparing effect when supplementing with a carbohydrate, which may have implications for endurance performance. And what also is nice about this study is we tagged on the 3-kilometer time trial performance at the end, which allowed us to quantify exercise performance. And despite that reduction in liver glycogen use during exercise, actually there was no difference with carbohydrate supplementation in the fed or fasted state or placebo in the fed or fasted state, which fits with some of the data that Claire presented earlier in the fact that carbohydrate doesn't seem to provide this benefit in terms of exercise performance. But saying that, should we advise people not to consume carbohydrate? No, I don't think we're at that point. We're seeing some really interesting data in terms of trying to get underneath the mechanism and the fuel kinetics of what's happening at altitude and how that's manipulated by different moderators, and whether or not carbohydrate supplementation can help with that or not. But ultimately the recommendation, Paul, as it stands at the moment until we know more is that yes, you should eat breakfast, you should consume carbohydrate as an additional source of fuel during exercise at high altitude. That's likely to assist in maintaining or at least trying to attenuate any reduction in lean body mass, which is associated with appetite suppression at altitude. It will also help with things like maintaining immune function, and has potentially been associated with the reduction in susceptibility to acute mountain sickness as well. That's a quick whistle-top tour of some of our work to date. We have some more work in the pipeline, particularly dealing with that issue of ecologically relevant altitudes for more sort of athletic populations rather than military personnel or mountaineers going to extremely high altitude. So thanks for listening, and just take the opportunity to share a picture of our brand new home for the Carnegie School of Sport, which will be opening for us to use, and our new set of research labs in September. Thank you.
All right, thank you very much, John. I guess I'll start with a kind of a general question that might be relevant to Claire also, but in terms of the kind of some of the studies that have been done, obviously you're specifically looking at fasted and versus non-fasted, but what is the impact of kind of just their, if they're going to be up there for in your studies for a week or whatever, their normal daily kind of diet is that also changed kind of within your studies to match kind of a higher kind of carbohydrate availability, or is it kind of relatively similar in composition to their sea level kind of over those, for example, 7 days?
Yeah, so I mean, obviously we know we go to altitude as an appetite suppression, so we'll develop a negative energy balance over a period of time. We've not within our studies included a negative energy balance in the run into them, very much because of the fact that acute exposures might not necessarily always happen in a negative energy balance. You might end up going in where you've been in a positive energy balance. So we've always maintained positive energy balance within our research. And there may be differences in terms of a negative energy balance, but then if you go in negative, then there's this potential that you might become fat adaptive. And, you know, we have just dealt at this moment with acute exposures. Chronic exposures is a slightly different story. And there's probably less work on that, but then it's complicated because you need access to a, you know, terrestrial altitude and somewhere nice where you can house people for a prolonged period of times. And Lee and Claire and Andy Young's group have done those nicely with Peaks Pike and been able to house people for 22 days. And so there's a lot more work that needs to be done for sure.
All right, great. And I'm gonna pass it on to Lee to get, because some of the questions are really excellent in terms of overall discussion. I think all three of you would contribute to nicely as a panel. So thank you very much, John. And I will pass the stage on over to Lee Margolis from USARIEM for the third talk in today's webinar.
Thank you very much for the invitation and allowing me to present my work, the work from USARIEM. So I'm Dr. Lee Margolis. I'm a nutrition physiologist, and I'm going to be talking about the effects of altitude exposure on exogenous carbohydrate, where we match absolute exercise intensities. So these are my disclaimer. I'm a government employee. So as John very nicely pointed out, that depending on if you are matching your exercise intensity under normoxic conditions to hypoxic conditions based on a relative or an absolute workload, you potentially are going to get very different results in total carbohydrate oxidation and its impact on endogenous glucose oxidation during exercise. What's nice is that his lab is very focused on looking at relative exercise intensity matching, while our laboratory is interested in looking at matching for an absolute workload. Like John showed, there is pretty limited data on the impact of exercising at high altitude with carbohydrate feeding. So the fact that their lab is looking at one half of the picture and our half is looking at the other half, it's nice that we're able to kind of join our findings and give the complete picture to our audiences. So like I said, we're interested in trying to understand the impact of exercise when it is matched for an absolute intensity. I'm going to primarily focus on two protocols that we've recently conducted at USARIEM. One was conducted at Pikes Peak, and it had 3 phases to it. We had our sea level component, then acute high altitude exposure, and then a chronic high altitude exposure, which occurred after 21 days of acclimatization at high altitude. Based on the findings from the acute study, we did a follow-on investigation where we conducted, essentially we matched our protocol looking at acute high altitude exposure in our hypobaric hypoxic chamber at USARIEM. So what I'm going to do is present the acute high altitude findings from our first study at Pikes Peak. I will then show the follow-up results from our hypobaric hypoxic study that we conducted in Natick, Massachusetts at USARIEM. And then I'll present the chronic high altitude data from our initial study that was conducted at Pikes Peak. So on our protocol days in the first study, the participants were exposed to hypobaric hypoxic conditions for 5 hours prior to the start of the exercise bout. So this ensured that they were quite hypoxic by the time they started exercising. They then completed 80 minutes of exercise that was set at 55% of VO2 max at high altitude. So at sea level, this equaled about 4 miles per hour at a 2% grade, and at high altitude, this was 3.6 miles per hour at around a 2% grade. During the exercise bout, they were fed 1.8 grams per minute of carbohydrate as a mix of glucose and fructose. We used a stable isotope methodology like John talked about, enriching the beverages with the C13 glucose. We unfortunately only enriched with glucose and not fructose, so we weren't able to capture the complete oxidation rates during this investigation, but we can report what happened with exogenous glucose oxidation. The exercise bout was performed on a treadmill, and we took breath and blood samples throughout. So comparing our data to at acute high altitude exposure compared to sea level, we saw a roughly 50% reduction in exogenous carbohydrate oxidation during the exercise bout, exogenous glucose oxidation during the exercise bout. So quite a significant reduction. And though we didn't see an increase in total carbohydrate oxidation, which you would normally expect when matching exercise for an absolute intensity, we did see no difference in total carbohydrate oxidation. So it does seem that even though carbohydrate oxidation is maintained, that the body's ability to use exogenous glucose during an exercise bout is blunted at acute high altitude exposure compared to sea level. It seems that there might be some sort of hypoxic-induced insulin resistance, which may be causing the lower rates of exogenous glucose oxidation during exercise at high altitude compared to sea level. What we found in our time course blood draws during exercise was that concentrations in glucose and insulin both rose significantly higher and did not return to baseline values during exercise at acute high altitude exposure compared to sea level, which the increase was much lower and its ability to return to baseline values was maintained at the end of the exercise bout. So this may suggest that there is some physiological decrement that's blunting peripheral tissue from being able to be insulin sensitive, take up that exogenous glucose that was consumed during exercise, potentially resulting in the lower exogenous glucose oxidation rates that we observed. There were, however, some methodological issues with this analysis. So, like I said, we only enriched the drink that had glucose and fructose with only C13 glucose, so we weren't capturing the entire picture. There was a lack of glycogen normalization prior to the testing, so glycogen stores being different before exercise bouts may have impacted some of our results. There's obviously discrepancies in looking at absolute versus relative workloads. Dr. Young's paper, which was the data that I just presented, was really the first to show a significant reduction in exogenous glucose oxidation when matched for an absolute workload. So there's a need to confirm those results. And then we need to kind of better understand what is the underlying mechanism that might potentially be causing this decline in exogenous glucose oxidation. So like I said, we conducted a follow-up study. This one was done in our hypobaric hypoxic chamber located at USARIEM in Natick, Massachusetts. We used the exact same protocol design as far as having the participants be under hypoxic conditions for 5 hours prior to initiating the exercise bout. Again, we used treadmill exercise at 55% of VO2 max. This time speeds were matched at 3.7 miles per hour, and the percent grade was 2% on the treadmill under both conditions. We only fed glucose this time at 1.8 grams per minute. The reason that we only provided glucose was we added a 6,6-T glucose infusion to this protocol so we could get a better understanding of glucose turnover to try to get to the mechanism that might be causing this. And again, we enriched our drinks with C13 glucose because we only provided glucose in this beverage. And throughout the exercise bout, we did our breath and blood draws again. What we saw in this study was that we did have an increase, almost a twofold increase in total glucose oxidation during exercise under high altitude conditions during sea level conditions. And quickly, I'd like to point out to the right here, the back of the person's head is Dr. Andrew Young. He wanted to make sure that I let everybody know that. And the most important part of my talk is that he still has all of his hair. He wanted to make sure that everybody was aware of that. Similar to our findings in our Pike Peak study, we did see again a reduction in exogenous glucose oxidation during the exercise bout. This time it was only a 30% reduction versus a 50% reduction that we saw in our initial study. The potential differences could be because we had an increase in total glucose oxidation during our follow-up study where glucose oxidation was maintained under acute high altitude conditions compared to sea level in our initial study. Regardless of the discrepancies in the percent declines, both studies are significantly lower at acute high altitude exposure compared to sea level. So we were able to indeed reproduce that exogenous glucose oxidation is diminished when exercising at acute high altitude compared to sea level. We were able to show that the increase in total glucose oxidation is primarily driven through increases in endogenous glucose oxidation, which obviously makes sense. If exogenous glucose is going down, endogenous needs to be going up if total is going up. This is primarily driven by increased oxidation of muscle glycogen, with no difference in liver glycogen between the two trials. And the increase in glycogenolysis appears to be confirmed with our blood lactate data, which was significantly increased under acute hypoxic conditions compared to sea level. Now looking at our stable isotope infusion methodologies, looking at the glucose rate of appearance, what we were able to see with these tracer studies was that there was an overall total reduction in the rate of appearance. This reduction appears to be primarily driven by lower exogenous glucose rate of appearance, which may suggest that there is a reduction in either the uptake or release of exogenous carbohydrate from the gut during exercise into circulation. So that could potentially contribute to the lower exogenous glucose oxidation rates that we observed during our study. However, when we looked at the area under the curve for the plasma C13 glucose, which could only come from our beverage that we provided during exercise, we saw a similar trend in the direction of the data that numerically it was lower at high altitude compared to sea level, but it wasn't statistically different. So this could indicate that reductions in absorption and release of exogenous glucose from the gut may partially contribute to lower exogenous glucose rates, but isn't likely to be the primary factor causing the decline. Again, looking at markers of insulin resistance, we see evidence of hypoxia-induced declines in insulin sensitivity. looking at the bottom two figures, the gray bars being high altitude and the black circles being sea level, we again see that there is an there's an increase in glucose concentrations and insulin concentrations when consuming carbohydrate during exercise at high altitude compared to sea level conditions. This time we have our stable isotope methodologies on board as well. So we're able to show that there's also a reduction in glucose rate of disappearance and molecular clearance rate. So the amount of glucose that's actually being taken up and being used in the muscle appears to be lower. These are common in insulin resistance or diabetic individuals. So it does appear that there is some reduction in insulin sensitivity at peripheral tissue upon acute high altitude exposure in these native lowlanders that may have contributed to the reductions in exogenous glucose oxidation that we observed in both of our studies. So now shifting back to our Pikes Peak study and looking at the chronic high altitude data, this was 21 days of high altitude exposure. We controlled exercise and feeding during this investigation. It is important to note that participants were in a energy deficit throughout their time at high altitude. This ended up being about 70% of total energy needs, so a pretty severe deficit. This was the result of a combination of increased energy expenditure and decreases in energy intake. And this ultimately resulted in an 8-kilogram weight loss over that 21-day period. So it's important that when we talk about this chronic high altitude data that it is in the context of following a combined high altitude exposure and energy deficit exposure. What we saw after 21 days of altitude exposure, shown by the yellow line here, is that we see similar increases in glucose and insulin concentrations that are more aligned with the sea level versus the acute high altitude. They aren't completely back to sea level values, but you can see by the letters being similar between them that they're not statistically different from one another. So there does seem to be some mechanism by which insulin sensitivity may be improved after chronic high altitude exposure. Also, this needs to do with the caveat that energy deficit could have also contributed to these findings. With the lower increases in glucose and insulin concentrations, we saw that exogenous glucose oxidation, though it was still lower in a gram per minute than sea level at chronic high altitude, in comparison to acute high altitude, it was able to significantly increase. So again, it seems that there is some mechanism that's allowing for exogenous glucose to be more readily used upon a more prolonged exposure, also with the caveat that energy deficit could potentially play a part in this as well. Now, even though the absolute value of exogenous glucose oxidation remained lower at chronic high altitude compared to sea level on day 21, we saw a significant reduction in total carbohydrate oxidation during the exercise bout. So the amount of carbohydrate needed to fuel performance was lower during chronic high altitude. With this, we saw an increase in fat oxidation at chronic high altitude as well. So it seems that under our experimental conditions, the participants were able to have some adaptations where they're more readily able to use fat during exercise, which resulted in a reduction in total carbohydrate oxidation. So because total carbohydrate oxidation was lower at chronic high altitude compared to acute and sea level, when we look at the exogenous oxidation as a percentage of that, we see that there's no difference at chronic high altitude being 27% of total carbohydrate oxidized to sea level, which was 22%. So it seems that even though the absolute value was still statistically lower when you account for total carbohydrate oxidized, that it was actually able to completely recover by 21 days of high altitude. It's important to note that we didn't do a time course in these experiments during this investigation, so it's possible that this adaptation may occur sometime between day 1 and day 21 of altitude exposure. It's also, again, possible that energy deficit played a part in this, so we don't know if we would have the same findings if individuals were able to maintain energy balance for 21 days, if we would have gotten the same substrate oxidation results. Though it is important to note that hypoxia-induced anorexia is pretty typical with high altitude exposure. So looking at a real world condition, it is unlikely that individuals would be able to maintain energy balance with being unacclimatized and then going into high altitude exposure. So we think that these results do mirror kind of a real world scenario more than trying to maintain energy balance throughout the 21 days. So what we were able to see in these two studies was that exogenous glucose oxidation is lower during aerobic exercise that is matched for the absolute workload with acute high altitude exposure compared to sea level. This occurs despite total carbohydrate oxidation being the same or lower, or higher at high altitude compared to sea level. So this would indicate that there is some sort of physiological adaptation that is causing this reduction in exogenous glucose oxidation. Based on our glucose tracer studies and the changes in circulating insulin and glucose, it appears that hypoxia-induced insulin resistance at the peripheral tissue is the underlying cause that is reducing exogenous glucose oxidation. And it appears that chronic high altitude exposure is able to alleviate the impaired glucose oxidation, but the time course for this remains unclear. So with that, I'd like to acknowledge my co-investigators and technical staff who supported these two studies. And I'll take any questions at this time.
Thank you very much, Lee. The three studies really nicely investigate the question from a variety of angles, and also it's also nice that they come up, it seems, with different conclusions in some cases. So I guess the first question, I wasn't clear if you clarified in your studies whether there were male and females, or was it all males?
I apologize. Those were all male participants.
Okay. So maybe we can lead off the question with what seems to be a common theme for some of the posed questions is, can each of you kind of discuss, what your best guess is about whether there are kind of true differences between males and females, and what some of the underlying physiology might be, and also where we might need to go in order to really study that. So Lee, maybe you can kick that off.
Sure. So certainly under sea level conditions, men and women are going to oxidize carbohydrate and fat differently during exercise. So it is possible that how they are using fuel during exercise at sea level is going to have some impact on what changes they might see under acute high altitude scenarios. And John was able to show that in a little bit in his studies. And I think he took the right approach where he separated out men and women right now, trying to get a strong understanding of what happens in a cohort of men and a strong understanding of what happens in a cohort of women. Once we're able to better understand if there are differences and if those differences would result in maybe different interventions required based on sex, then doing a larger study where you power for examining sex differences would be appropriate at the time.
Great. Thanks, Lee. John, would you care to jump in on anything?
Yeah. No, I mean, I concur with Lee. I think we need further research, and that's not a cop out, because we can all say that with a whole host of things. But I think is if you were to ask me, looking at the original literature, what the differences might be, then you would come back to some of the sea level mechanisms in terms of what we already understand in terms of higher fat oxidation in women compared to men at sea level, in terms of greater adipose tissue stores and the hormonal aspect of fuel utilization compared to men. But since we've then compared men and women directly, the fuel use mechanisms, it seems the fuel selection or partition at altitude is very, very similar. And therefore, there's further investigation is really needed to try and understand whether or not there's a different mechanism of effect, i.e. is there a ceiling for fat oxidation? Women just can't push through that, whereas men are starting much lower. So I think we need some more mechanistic studies and some more direct comparisons to be able to answer some of those questions, acute and chronic studies, I would add.
Great, thanks, John. And Claire, would you care to provide any thoughts?
Sure. I'll just add, not as much from substrate utilization, but more with energy use. We see differences between, or some of the early studies have seen differences in the increases in basal metabolic rate between males and females. So some of those early studies, the Butterfield study, and then the study by Mawson. So Butterfield looked at men and energy balance and saw an acute increase in basal metabolic rate of 27% initially, whereas they only saw about a 6 or 7% increase in women's basal metabolic rate upon initial ascent. And obviously there's been other studies done, but those were done by the same research group, and just shows some differences in the magnitude of response in men versus women. And then when we come back to energy recommendations, a lot of times we'll see, well, males need at least 500 more calories per day to cover just the increase in BMR, whereas women, their needs are attenuated a little bit. They usually say 200 to 300 calories per day to cover those increases in basal metabolic rate. So that could be due to body size somewhat, certainly, but just interesting from the total energy package that there are these differences as well.
Great, thanks for that. And the other kind of theme of some of the questions we've received is really kind of what counts as acute, what counts as chronic, and then extended to that, what about, or what knowledge do we have or know about that we can discuss from kind of long-term and indigenous populations to high altitude? Maybe we can go into reverse. Claire, do you want to start off with kind of if you know of any kind of research that can kind of inform that discussion?
Sure. So I think if you took each of us separately and asked our definition of acute versus chronic, it would probably be different. So I guess I'll take the cop-out answer and say acute is like the first 3 to 7 days, and then base that on attenuation in BMR that we see at about 6 to 7 days. But certainly you could argue for ventilatory effects that adaptation happens sooner than that. So that's kind of a wide range, I know. And then anything past the acute effects, I would call chronic effects. Most of the studies have looked at, a lot of studies have looked at high altitude exposures for up to 3 weeks. But the chosen amount of time for those chronic exposures do vary, and I'm not sure what the basis is for selecting that length of time. I know in our study, the basis for selecting that was the amount of time that military personnel can subsist on the combat rations, solely on the combat rations. But in other studies, they've also selected about that amount of time for chronic exposure. And as far as indigenous populations, I'm sure there's research out there on the macronutrient content of their diets, but I can't pull it off the top of my head right now. But as far as body composition, indigenous populations typically have lower muscle mass than sea level natives. This is just a general trend that I've seen in the literature.
All right, John, any feedback or ideas?
I agree with acute and chronic definition. So yeah, I think acute stuff is up to around up to 3 days, and obviously you're looking at the physiological adaptations beyond fuel use to be able to help you define those periods of time. But I agree with Claire on the definitions there. Indigenous populations, I think there may be 1 or 2 papers which have looked not at looking at indirect calorimetry of indigenous populations, but have looked at some genome type work, which have then suggested that they may be more efficient at burning certain types of fuels, but I can't think of the references off the top of my head. I'll have to go back and have a look. But the reality is they're more efficient at altitude, so they will have found and developed a very strong ability to operate with significantly less oxygen, so they'll be more efficient at burning carbohydrate, I'm sure.
Okay, and Lee?
Yeah, again, I concur with the definitions for the acute and chronic. And yeah, I just think that, like I highlighted in my talk, we need to have a better understanding of the time course for some of the substrate oxidation changes when we look at exercise or hiking with some sort of feeding protocol involved in that. So we might be able to get a better picture of when shifts might occur with the efficiency of using exogenous carbohydrate oxidation that might allow for a more tailored recommendation for feeding at high altitude. Though certainly right now best practice is carbohydrate and consuming the foods that you can tolerate with any AMS conditions.
Yeah, well, sounds like we have a good idea for a future symposium, and I know Phil Ainsley posed that question, so I'll start bugging him to think about that. Any kind of closing thoughts from everyone about just, I guess, if you were to design, let's say, the next study, like what would it be? Maybe I can ask it in terms of future research that way. Any of you want to start that off? Like, what would be the research question? What would kind of be the main focus?
I think for me at the moment, the research question would be to look much closely at what's the mechanism where we, in terms of fuel selection at altitude. So it'll be to design a study which has an acute and chronic element to it, so we can track that over time. But would be to, would look at probably replicating some of the protocols we've used with carbohydrate supplementation during exercise, but moving that on with muscle biopsy work to be able to start to look at the regulators rather than us just looking at indirect calorimetry and 13 carbon tracing techniques, and is to combine all that together. That's where I would see some of our work potentially going in the future. But I also think Trent Stellingworth makes a really good comment in his review article around we focus very much on high altitude based on Pikes Peak being at 4,300 meters and an interest in military personnel and mountaineers. There is probably some relevance for us to start looking at more ecologically relevant altitudes around 2,500 meters for athletes that go to holding camps and training camps, and whether or not some of their nutritional recommendations need to be altered slightly to accommodate any changes in fuel selection we might see at those altitudes.
And Lee, what would be kind of the next question that you really want to address?
Yeah, so I'm very interested in trying to address the reductions in exogenous glucose oxidation, try to understand what intervention we might be able to implement to either reduce that negative effect or is there a different substrate that we may be able to provide as an alternative fuel source to fuel the body during exercise? Even though we don't know how long this persists, when we think about military operations, there is a need to support soldiers, service members during, a very, very acute altitude exposure without much time or any time to acclimatize. So if we can come up with an acute intervention to minimize negative effects and hopefully help maintain performance a little bit better, that would be what our lab is most interested in.
Great. And Claire, final thoughts go to you.
I'll finish it off here. Yeah, so my research interests are moving a little bit away from human performance and more towards human health. And so my next step would be the interest in looking at high altitude exposure, either normobaric or hypobaric exposure in normal weight individuals versus individuals who are overweight or obese, and looking at substrate utilization in those individuals, and also energy expenditure, changes in weight, if hypoxia can be used to benefit glucose regulation or insulin sensitivity. So all of those good things. So I think together we have some pretty diverse interests in future directions.
Great, super. So again, I want to thank all of our speakers for some really excellent talks. I know this was a very highly focused talk, and I love how, there was, even within that focused question, there were so many kind of ideas and thoughts that branch off from that. So I will just, again, finish off, share my screen here, just to mention that, again, I want to, on behalf of the organizers and all the attendees, thank Claire, Lee, and John for an excellent session. And I want to thank Andrew Young also for giving us this idea for this session to begin with. And just to finish off, just want to, if you have time, to please go to ICE2021.com, and you'll see at the top there the feedback survey. If you could give us some feedback about how you found some of the talks so far, help us plan for the future when we have, again, one more session on July 16th, and then we're going to take a break until September, but we like to cater these talks to you and your interest and your kind of what you want to get out of them. So if you can give us feedback, that would be terrific. So I hope you enjoy the rest of your day or evening, depending on where you are. And until July 16th, take care and have a great day. Thank you very much.
Thank you.
Thank you.